Hi, I'm Tom Beebekauser with Wetland Restoration and Training. I'd like to show you how we removed a dam and restored a valley near the community of Trail in British Columbia, Canada. Let's get started.
This is Cambridge Creek Lake. Cambridge Creek Lake is a reservoir that was built to supply water to the city of Trail in British Columbia, Canada. The dam for the reservoir was built across Cambridge Creek, which drains north into the Columbia River. The Cambridge Creek Reservoir is located south of the city of Trail. The area surrounding the lake has been closed to public motor vehicle access for years to protect the water supply. This drawing from 1911 shows there were two small dams on Cambridge Creek before a much larger dam was built to supply water. The area labeled as a lake was a small reservoir used to power a sawmill. A smaller dam created a log pond where logs were soaked, sorted, and floated downstream to the sawmill. The sawmill was used to process the abundant western hemlock, western red cedar, white pine, and Douglas fir trees in the valley. In 1918, the two sawmill dams were replaced with a larger dam as part of a system to provide drinking water for the city of Trail. This engineering drawing from 1917 shows the dam that was built to supply water. Development of the water system also involved building a dam across nearby Goodeve Creek, the outlet for Violin Lake. A future video will show how we removed the dam and restored Violin Lake. The dam built across Cambridge Creek was 8 meters high and 196 meters long. The Cambridge Creek Dam created a reservoir that was 7.41 hectares or 18 acres in size. The dam was built with a concrete core that was based on an impermeable layer of bedrock. This engineering drawing shows a typical profile view of the designed dam. Later, when we removed the dam, we did not find the 6-inch tile drain or the steel sheet piling. The hard pan shown on the drawing ended up being bedrock. It was necessary to make the core out of concrete because clay soil was not available for building the core and the groundwater dam. The Cambridge Creek Reservoir Dam was rebuilt in 1967. The dam was armored with a thick layer of rock so that waves would not cause erosion and to protect it from muskrat and beaver burrowing activity. Very few dams are armored with rock because of the high cost of this practice. In 1994, the city of Trail changed its source of water from the Cambridge Creek Reservoir to the Columbia River. The city of Trail stopped using water from the Cambridge Creek Reservoir system due to concerns about water quality. The Cambridge Creek Dam required constant monitoring and frequent maintenance. Beavers would continually block the emergency spillway of the dam with branches, trees, and soil that had to be removed. The dam could fail with runoff from one major storm if the spillway was blocked. The city of Trail erected a 24-hour remote video camera to monitor the spillway and the dam on the Cambridge Creek Reservoir. This was advanced technology in the year 2018. The Cambridge Creek Reservoir and Violin Lake dams, along with associated infrastructure, were old and in need of expensive repair and regular maintenance, which was a significant and increasing cost and liability for the city of Trail. The city of Trail determined that the cost of continued operation and maintenance of the dams outweighed the benefits and decided to remove the dams and to restore the area's natural lake, wetlands, and streams. The British Columbia Wildlife Federation worked in partnership with the city of Trail to design, plan, and implement the removal of the Cambridge Creek Reservoir and the Violin Lake dams. John Howes, the engineering technician for the city of Trail, was instrumental in making the project possible. Obtaining approval to remove the dams involved a very complex and time-consuming process, with 11 different permits being required by provincial and federal agencies to move forward with the project. This would be one of the first dams removed under the new British Columbia Dam Safety Regulations. The funding needed to implement the project was received from the British Columbia Healthy Watershed Initiative Program, Investing in Canada Infrastructure Program, and the City of Trail. One of the first steps in construction was to drain water from the reservoir. I recommended simply keeping open the valve in the drain pipe that had been installed years ago. The valve was in a concrete box on the backside of the dam. Some individuals didn't want us to keep the valve open. They thought the dam would wash out if water continually flowed in the drain pipe. Following discussions with City of Trail employees who had been maintaining the dam, combined with my experience of installing and repairing drain pipes for many years, we agreed it would be safe to drain the reservoir by opening the valve. We opened the valve in May of 2020 and drained the reservoir. This was done prior to decommissioning the dam in the summer of 2021. Water drained from the reservoir without causing any damage to the dam. A pool of water remained near the inside toe of the dam. The surface elevation of water in this pool was lower than the base of the dam and at the entrance to the drain pipe. This pool may have formed after soil had been removed to build the dam. We recommended keeping water in the pool and reshaping its shoreline so it would appear like a natural wetland. This drone image shows the drained Cambridge Creek Reservoir. The small pools of water may have been beaver ponds. The area of parallel ridges may have been formed by a dozer that was pushing soil to make the dam. Our inspection of the drain basin revealed the probable location of beaver dams. Saws and axes had been used to cut holes in the beaver dams before the area was flooded. This was probably done to drain the swamp so the large cedar trees could be more easily harvested. We found where an old road had been built across the basin that may have been used for logging. The road, called a corduroy road, was built by placing soil over a row of logs to provide access across the soft, organic soils. Headcuts formed, causing significant erosion while the reservoir was being drained. This photo shows how a headcut is causing the significant deepening and the widening of a historic stream in the valley. The red arrow marks the headcut and the direction it's moving. Note that there is no stream channel with a stream bed or banks upstream of the headcut, but there is a deep and a wide channel downstream of the headcut. Here's how the stream should have looked in the dry basin. Water historically would have been flowing across the surface in a sheet-like pattern. Prior to construction of the dams, much of the basin was wet meadow with saturated soil. The streams had low banks with no defined channel. People illegally riding dirt bikes in the basin were creating channels in the saturated organic soil. Their tire tracks quickly formed ditches. The tire ruts were creating ditches and headcuts. The ditches were draining wetland pools and lowering the elevation of groundwater. The muddy basin had become a playground for dirt bike riders. We observed how some of the logs that had been buried in the basin before the dam was built were now preventing headcuts from moving upstream. We decided we would purchase large diameter logs and bury them across the floodplain of the streams in the basin to control headcuts that were causing so much erosion. Let's fly over the basin of Cambridge Creek Reservoir to see what's been happening since the drain pipe was opened to drain the reservoir. The green plants are bidens and smartweed that are growing on the dried floodplain. There's an old beaver dam that was breached by humans. Cambridge Creek is eroding a channel in the organic soil. The stumps are from western red cedar trees cut before the valley was flooded. There's another breached beaver dam just before the mudflats. The headcuts are wide and deep in the saturated organic soil. The stream is eroding a deep channel. On the right side of the valley, there are hundreds of ruts that were made by dirt bikes. The shallow pools of water were beaver ponds of various sizes that were present before the Cambridge Creek Dam was built. There are many headcuts that are advancing upstream that are causing erosion and making the banks of the stream vertical. These headcuts were triggered by draining the reservoir. The white-colored ridge that goes across the basin and is perpendicular to the stream is an old road that was probably used for logging. The light-colored soil with parallel ridges on the right side were probably made by dozers pushing soil to make the dam. The basin was very difficult to walk in because of the deep mud. The narrow ridge on the left side of the pool is rocky soil that was not used to build the dam. The pool has straight edges showing where soil was removed to build the dam. The dam spans the entire width of the valley and is armored with rock to protect it from waves and from muskrats and beaver that would have burrowed into the dam. One of our biggest challenges was determining how much of the dam to remove. This sounds easy, but the plans from 1917 didn't show us the historic elevation above sea level in the valley where the dam was located. And we could not see the upslope toe of the dam because of the deep water in the reservoir. We tried using measurements taken from a boat to estimate the elevation of the valley before the dam was built. We were better able to accurately determine the original elevation of the valley before the dam was built after water had been drained from the reservoir. We did this by measuring the elevation of the ground at the base of a large western red cedar tree stump. The tree had been growing on the bank of the stream before the dam was built. We drove a stake into the ground to serve as a benchmark for stream construction. The elevation at the top of the stake was set to match the inlet elevation of the stream that would be built after the dam was removed. We then determined where and at what elevation the restored stream would flow into the beaver pond downhill of the dam after it was removed. To design the new stream, we calculated the slope from where the flow would start across the removed dam to where it would exit the former dam area. Robin Anstild, Miranda Cross, and I prepared the designs for the Cambridge Creek and Violin Lake Dam Removal Restoration Project. Our designs were reviewed and approved by an engineer. The presence of western red cedar stumps that had been underwater for over 100 years showed us which portions of the basin had been swamps. Our team selected a business named Sublatis from Calgary, Alberta, to provide 2 large excavators, 1 dozer, and a wheel loader with skilled operators to complete the project. We saved a significant amount of money by paying Sublatis hourly for each piece of heavy equipment with a skilled operator that was doing productive work. Robin Anstild, Miranda Cross, and I were on site 100% of the time working with the heavy equipment operators in what needed to be done. Our first action in construction was to improve the mountain road so we could access the Cambridge Creek Reservoir without damaging our vehicles and so that the dump trucks could drive on it to haul rock and coarse woody debris. The road was narrow and extremely rough with saturated sections that prevented access by tandem dump trucks. We spent 5 full days of work with 1 excavator and 1 dozer prior to the start of construction improving the road. This was followed by regular maintenance throughout construction. Because the road was too narrow for two-way traffic, we also constructed a series of pullouts and established call signs so that multiple trucks could safely travel up and down the road at the same time. Road maintenance involved using heavy equipment to remove boulders, do widening, remove fallen trees, improve drainage, regrade the surface, and apply gravel. As construction continued, the dozer operator periodically regraded the road, and we added gravel where needed to maintain safe and reliable access. Here we're measuring and marking the location of the floodplain that will be built for Cambridge Creek that will help guide the heavy equipment operators as they remove the dam. The main way of controlling erosion during construction was to keep the drain pipe in the dam open so water would not flow over exposed soil during construction. To increase capacity, we used an excavator to remove the flap and the grate attached to the inlet of the drain pipe. Some people think that by placing a grate over the entrance to a drain pipe, it will protect it from plugging. The opposite is true. 2 trash pumps were placed near the entrance to the drain pipe and used to lower the water level in the pond at the base of the dam. Lowering the water helped dry the soil along the edge of the dam, reducing the risk of the dozer becoming stuck. The pump discharge hoses were routed into the drain pipe so they would not interfere with dam removal activities. We kept the drain pipe in place and protected it from damage until the dam was removed and the stream over the dam had been built and armored with rock to prevent erosion. Construction began with excavators removing and salvaging the many tons of rock that had been used to armor the dam. The rock was moved and placed in stockpiles outside of the areas where the stream would be restored or where soil would be spread following dam removal. Salvaging this material saved tens of thousands of dollars by eliminating the need to purchase rock from a quarry and haul it to the site on a narrow access road. We were not concerned about rock being mixed with soil. Dirty rock is easier to embed into the ground, and plants will readily establish in the narrow gaps between the stones on the restored stream floodplain. The dozer operator is removing soil from the dam while both excavators finish salvaging the rock. The soil that made up the dam is being reused to fill the corners where the dam connected at right angles to the sides of the valley. This material is being shaped to create natural-appearing valley slopes. Project costs are being greatly reduced by pushing and shaping the soil with the dozer rather than loading it into dump trucks and hauling it off-site. The excavator is rapidly lowering the dam and placing the soil in front of the dozer to move it to higher ground. This pairing of an excavator with a dozer is a very efficient way of moving large quantities of soil up to 200 meters away. The excavator operator is helping to free the dozer that is stuck in the saturated soil. The dozer is a low ground pressure machine with wide tracks, so it didn't get stuck very often. The dozer operator was wise, waiting for help from the excavator to free it from the mud. The excavator works to expose one side of the concrete core in the dam so it can be broken into pieces using the breaker attachment on the excavator. The concrete core is exposed and cleaned of soil on one side prior to using the breaker attachment. We were now ready to begin removing the top of the concrete core to lower it to the target elevation and restore the historic elevation of the floodplain. The concrete core was a massive structure that spanned the width of the valley. The concrete core prevented water from leaking through or under the dam for over 100 years. Here the excavator uses the breaker attachment to shatter the concrete. The concrete was reinforced with small diameter rods. The breaker is like a giant jackhammer that's powered by hydraulics on the excavator. It shatters the solid wall of concrete into smaller pieces. The excavator cannot pick up and move the broken concrete while the breaker is connected to the machine. The second excavator uses a bucket on the machine to move the broken concrete out of the way so the excavator with the breaker attachment can continue dismantling the concrete core. 2 excavators are used because it would take a great deal of work and time to continually switch out the breaker with the bucket if only one excavator was used. We found one small crack and leak in the concrete core. This crack was not affecting the ability of the concrete core to hold water. The pink wire flags mark the width of the floodplain to be built for Cambridge Creek. The section of concrete core marked by the wire flags will be lowered to an elevation equal to the bottom of the stream channel we're restoring at this location. The lowered section of concrete core will be left buried under the restored stream and floodplain, and this will serve as a buried vertical grade control structure. The buried vertical grade control structure will help prevent head cuts from advancing upstream after Cambridge Creek is restored. A red-colored lumber crayon was used to show the excavator operator at which elevation to remove the concrete core where the floodplain of Cambridge Creek would be located. This drawing shows how a lowered section of the concrete core spanning the width of the floodplain was left in place beneath the stream being restored. Here's where the drain pipe carrying Cambridge Creek flowed under the dam. I found it interesting that the wooden form surrounding the drain pipe was preserved after so many years. The red crayon mark shows the excavator operator at which elevation to stop removing the concrete core. Here the excavator is removing soil to expose the upstream side of the concrete core. The red arrow marks a mound of soil that has been left over the drain pipe so water can keep flowing under the construction area while we're removing the dam. Removing the concrete core generated large quantities of broken concrete. Something had to be done with the large piles of concrete. We used the broken pieces of concrete to build a large snake hibernaculum. The snake hibernacula was built by digging a large and deep hole near where the dam was being removed. We selected a site on high ground in a sunlit location that was well drained so snakes using the habitat could stay dry. The hole was filled with both large and small broken pieces of concrete. We purposely left spaces between the rocks so snakes would be able to move in and out of the structure. To reduce the amount of soil that could filter down and fill the voids between the pieces of concrete, we placed a layer of thick paper material called ramboard over the piled concrete and then covered it with soil using the excavator. We carefully made an entrance to the hibernacula that water could not flow into during a storm. Boulders were placed near the entrance to the hibernacula for basking by snakes. Here, one excavator is digging the floodplain for Cambridge Creek while the second excavator continues removing the concrete core. Excavator operator Andrew Steen did an excellent job removing the concrete that was surrounding the drain pipe without damaging the drain pipe. Keeping the drain pipe intact allowed us to remove the dam without having to use larger pumps with long discharge hoses to keep the area dry during construction. Here, one excavator removes the dam where the floodplain will be located, while the other excavator moves the soil away from the edge of the hole so the dozer can safely push the soil to the edge of the valley. The dozer is pushing soil removed from the dam to one side of the valley. The excavator operator places soil where the dozer can safely get behind it and push it forward. The excavator is very careful not to hit the dozer. At the same time, the dozer operator ensures that the stockpiled rock that was salvaged from the dam is not covered with soil. Here's another view showing how the dozer and excavators are working together to remove the dam. The dozer operator shapes the soil from the dam to create a gradual slope on the side of the valley. We focus on making the floodplain for Cambridge Creek now that most of the dam has been removed. This drawing is a profile view showing the floodplain and stream channel as we're building after the dam was removed. The floodplain would be built an average of 15 meters wide and the stream channel approximately 2 meters wide. The excavator operator is building the floodplain for Cambridge Creek an average of 15 meters wide and level in cross-section. The laser receiver has been attached to the stick of the excavator to help guide the operator in building a floodplain on a 4.4% slope. The green light on the laser receiver shines when the bottom of the bucket is at the planned elevation for the floodplain. Here, the excavator is digging the stream channel for Cambridge Creek. The bottom of the stream channel will only be 15 centimeters lower than the elevation of the floodplain. Each year when the snow melts, water will flow out of the channel and across the floodplain in a sheet-like pattern and not cause erosion. We patterned the channel and floodplain dimensions for the restored Cambridge Creek after stable, natural sections of the same stream. Upstream of the drain basin, we found a reference reach with a narrow, shallow, sinuous channel and banks only about 15 centimeters above the water surface. The floodplain is saturated and covered with sedges, and during snowmelt, the flow spreads across the floodplain without eroding soil. The absence of head cuts and vertical banks shows this reach is stable and not incising. Our next step is to build a buried vertical grade control structure using large rock at the downstream end of the stream channel and the floodplain that we're constructing. The structure is needed to protect the stream we're building from being destroyed by major head cuts that are moving upstream. These head cuts formed when the beaver dams were breached downstream of the Cambridge Creek Dam. It's also possible some soil was dug out from downhill of the dam where the beaver pond is located to build the Cambridge Creek Dam. This would have lowered the base elevation of the stream and sent head cuts upstream that were stopped at the drain pipe. To build the buried vertical grade control structure, we first dig a deep and wide trench across the width of the valley where the restored stream will leave the project area. The excavator removes soil and wood scraps to dig a foundation for the buried vertical grade control structure. The excavator digs deep to remove wood, gravel, and soil until it reaches bedrock that will serve as a secure foundation for the boulders to be placed in the trench. The deep trench is being dug to span the entire width of the valley. The wheel loader operator picks up boulders harvested along the edge of the logging roads to bring to the excavator to place in the trench. The excavator operator picks up and moves the largest boulders to place in the very bottom of the trench. These boulders are carefully moved into position so they fit tightly together. This is a challenge because the boulders are placed underwater with limited visibility. Large rocks are fit into the gaps between the boulders, with smaller rocks being placed on top to form a riffle. Amber Peters helps guide the placement of the large rocks in the trench. The buried vertical grade control structure is built in the shape of a wedge with a narrow end downstream. The excavator operator uses the bucket on the machine to test to see if the rocks have filled the trench and pounds any rocks that wobble until they fit tightly together. The end of the constructed stream is shaped so there will be gradual slopes over the rocks in the vertical grade control structure. The operator uses the bucket on the machine to push smaller rocks into the ground, thereby armoring the floodplain and the stream banks to control erosion. The rocks being used to armor the stream channel and the floodplain were salvaged from the surface of the dam. We do final grading of the channel, floodplain, and stream banks to prepare them for armoring with rock to control erosion. The wheel loader moves rock that was saved to the excavators so they can spread the rock over the floodplain and in the stream channel. The excavators work together to spread the rock in a thick layer over the floodplain and in the stream channel. The rock is spread so that once pushed into the ground, the compacted rock layer will be at least 70 centimeters thick. Soil is intentionally mixed with the rock so that when compacted, water will flow across the surface of the channel and the floodplain rather than beneath the surface in voids between the rocks. Here the excavator operator uses the bucket on the machine to push the rock into the ground. The rock is also placed up the sides of the valley. This is done so that if beavers build dams across the restored stream, water will not flow around the edge of the armored floodplain and cause erosion. The laser level is used to make sure the floodplain is built level in cross-section and on the designed 4.4% slope. Boulders are also placed in the stream channel and on the floodplain. Large rocks are buried in the ground across the width of the stream and floodplain where water enters the restored stream from the pool that was saved. These rocks will prevent beaver from digging a canal down the length of the restored stream. The flow of water is changed from the drain pipe into the restored stream. The drain pipe that is no longer flowing water is exposed by the excavator. The excavator operators work together to remove the drain pipe. Final shaping of the floodplain and the valley is done now that the drain pipe has been removed. Small basins are created on the floodplain that will form shallow pools. The small basins have filled with water, showing the restored floodplain is saturated. We began spreading topsoil over the restored floodplain. The topsoil is mixed with roots and branches and not compacted. To reduce the chance of erosion, topsoil was spread over the floodplain and not in the stream channel. The stream channel and floodplain were built in the dry, without flowing water that would have caused erosion. We are pleased to see that the flow of water in the restored stream was not causing erosion. We used the rough and loosen technique to create a rough surface in the valley, and this was done to discourage people from driving off the road. The loosened soil also created an excellent substrate for plants to grow. We then used the excavators to spread large quantities of woody debris in the valley. The woody debris created excellent habitat for small mammals and was very effective in showing people they should keep their motor vehicles on the road. The restored stream and floodplain are ready for planting. Restoring wetlands and streams in the drain basin had become a very important part of the project. The objectives of the project included controlling erosion and resaturating the floodplain of Cambridge Creek, and this would be done to prevent the loss of stored carbon from decomposing organic soils. Unfortunately, most dam removal projects fail to address the erosion that occurs in the basin after the dam is removed. They also neglect to restore the wetlands and streams that were damaged or destroyed in the years before the dam was constructed, along with the wetlands and streams that were destroyed when the dam was built. The Cambridge Creek Reservoir had not filled with soil from erosion occurring upstream. We base this observation by seeing the roots of trees cut in the valley before the dam was built that had not been buried by sediment. We observed that some of the logs buried in the stream before the dam was built were preventing head cuts from moving upstream. Water was flowing over the logs that were buried years ago and not under or around them. This log that's along the edge of the stream is also controlling erosion. This drawing shows a side profile view of how we placed log structures in the stream to control head cuts and erosion and to help saturate the soil on the floodplain. Here's a front profile view showing how we placed the logs in the stream to control head cuts. We purchased large diameter western red cedar logs that were 40 feet long to use in building buried vertical grade control structures to control head cuts that were advancing upstream in the drained basin. The western red cedar logs would be rot resistant and last for many years. The excavator places the first log in a shallow trench dug between the white flags. The log is pushed into the ground using the bucket on the excavator. A second log is placed in the trench adjacent to the first log. Both logs are pushed into the soil so that water will not flow under the logs. The logs are pushed into the ground so that the top of each log is level. The downstream log is pushed into the ground more than the first log so that water will flow over the upstream log and splash over the second log. The excavator rotates the cab and scoops up a bucket full of plants and roots from where we'll be building the wetland. The bucket full of plants and roots is placed over one end of the log to help keep the log from floating. The sod is also less likely to wash away compared to using loose organic soil to hold it in place. The pile of sod is shaped and pushed gently into the ground to form a bank on the stream. A second bucket full of plants is placed over the other end of the log. The plants are pressed into the ground and shaped to form banks on both sides of the stream. The operator shapes a shallow stream channel so that water flowing out of the wetland will flow over the center of the logs and not around the logs. We found that some of the western red cedar logs we installed floated so that water flowed under and not over them. We tried repositioning and anchoring these logs with limited success. It would have been better to have used green-cut cedar, Douglas fir, or large trees because they're heavier and less likely to float. We also built several buried vertical grade control structures by mixing alder branches and soil like beaver do and burying this mixture in trenches dug across the stream channel. Here's one of the artificial beaver dams we made from alder and soil. An advantage of this technique is that it also raises the elevation of water in the stream. We had very good success controlling head cuts by using rock from the dam to build buried vertical grade control structures. The rock did not float or wash away. This drawing is a profile view showing how we used rock to control head cuts and to raise the elevation of water in the stream. The wheel loader would move the rock as close as possible to where the head cut was located without getting stuck in the soft ground. It was acceptable that some soil was mixed in with the rock. The excavator keeps logs under the machine to keep it from sinking as it moves into position to repair the head cut in the stream. The white flags show where to build the structure. The operator makes a temporary path of logs to drive on so it can reach the place where rock will be buried to build the structure. The log path will be used by the excavator to travel back and forth to pick up rock from the pile left by the wheel loader. The operator starts digging the trench that will be filled with rock. The plants and roots are removed and saved to place over the stream banks after the trench has been filled with rock. The sod is temporarily stored within reach of the excavator. The trench is dug from stream bank to stream bank. The soil that is removed is placed in a pile that will later be spread away from the stream. The bottom of the trench is dug so that it is at the same or lower elevation than the top of the nearest vertical grade control structure located downstream of the one being built. Rock is placed in the trench using the bucket on the excavator. The rock is moved so that it fills the trench. The bucket on the excavator is used to push the rock into the ground. Considerable force is used to pack the rock tightly together and to embed the rock into the ground. A gradual downhill slope is made where water will flow over the rock. The plants and roots that were saved are used to reshape the stream banks. The stream channel and stream banks are shaped so that water will flow over the center of the rock placed in the trench. The piled soil removed from digging the trench is moved away from the stream bank and the floodplain of the stream. The excavator places gradual slopes on the stream banks. More of the piled soil is moved away from the stream. Cambridge Creek flows over the buried vertical grade control structure that was made using rock. The buried vertical grade control structure is now a riffle in the stream that also prevents head cuts from forming that can cause erosion and dry the surrounding wet meadow wetlands. The vertical grade control structures repaired the incision in Cambridge Creek that gave the stream access to its floodplain during the spring freshet and resaturated the entire floodplain. We used the excavators and dozer to build wetlands of various depths and sizes in the drained basin of the Cambridge Creek Reservoir. The wetlands were built to provide habitat for a diversity of species, including the western toad, Columbia spotted frog, bald eagle, great blue heron, grizzly bear, moose, and beaver. Wire flags were used to mark the perimeter of each wetland we planned to build in the drained basin. We dug a test hole in the center of each wetland before building to measure the depth of groundwater beneath the surface. Here, the elevation of groundwater is about 1 meter below the surface. We would need to dig at least 2 meters deep in the middle if we wanted the wetland to contain water 1 meter deep this time of year. The elevation of groundwater in this test hole is about 2 meters below the surface. We would need to dig at least 3 meters deep if we wanted the wetland to contain water 1 meter deep this time of year. The laser level is set up outside of the marked area so elevations can be taken to guide the operator in knowing how deep to dig. The excavator uses the logs to keep from getting stuck in the wet ground. The excavator uses a set of 6 to 8 logs to keep the machine from sinking. The logs are picked up and moved in front or behind the machine depending on the direction it's traveling. The individual logs that break are placed in the wetland being built to improve habitat for wildlife. The excavator can stay afloat on very wet ground when using the logs. We found that the logs work much better than wooden mats when building a wetland using the groundwater technique. Logs must be at least 16 inches in diameter and 20 feet long. The logs should be cut from living and not dead trees. Logs cut from Douglas fir and larch are the strongest tree species to use. The wetland is dug deepest in the middle with pits and mounds to increase plant and animal diversity. Groundwater fills the basin as it's being dug. Here, Ted Crane got stuck when he tried to build a large and deep wetland without using logs to stay afloat. He skillfully used the bucket to pull the machine out of the mud and then used the logs to keep the machine from sinking as he built the largest wetland for the project. Here's the large and deep wetland Ted Crane built. He placed the mound so it would look like a beaver lodge and spread much of the soil with the excavator. The wetland filled with groundwater within 2 days and should provide excellent habitat for moose. This is the wetland Ted built 1 year after construction. The wetland he built is the first one where western toads were observed breeding, and in only 1 year after construction. 2 excavators are working together to build a wetland. The machine on the left is digging and shaping the wetland, while the machine on the right moves soil to higher ground. The soil is placed so that it does not block runoff from entering the wetland. These 2 excavators are working to build another wetland. The excavator on the left is transferring the soil to higher ground. We built the wetland in the foreground earlier in the day. Logs and stumps were placed in and around the wetland to improve habitat for wildlife. This photo shows a natural wetland near Cambridge Creek. We worked to restore wetlands in the drain basin of the reservoir that would appear and function similar to this one. Here's a natural forested wetland or swamp near Cambridge Creek. We worked to restore forested wetlands like this one. Here's one of the wetlands we restored the same day it was built. Notice the pits and mounds and woody debris, and these will form the foundation for a naturally appearing and functioning forest wetland to develop. This is another wetland we restored the same day after it was constructed. These restored wetlands are quite unlike the artificial impoundments that are being built by other nonprofit organizations that have dams, berms, pipes, and water control structures that look artificial and must be maintained. The wetlands were restored to have various shapes, sizes, and depths to provide habitat for a diversity of plant and animal species. Snags were placed by the excavators to provide birds with perches. I would like to show you how Andrew Steen made it look like a large western red cedar tree like this one fell naturally into a wetland. The process begins by using the excavator to pull up the stump of a western red cedar tree. A stump is chosen where the trunks of the trees are roughly the same diameter. The stump is dropped near the large end of the log we want to place in the wetland. He is careful not to remove the soil surrounding the roots in the stump. Next, we dig a hole in which to place the roots of the stump. It just happens that he must remove the roots of an old tree from the hole that he's digging to make room for the larger stump. The hole is dug large enough so that it will look like one half of the root mass came out of the ground when the tree fell over. The sides of the hole are shaped and sloped to match that of the hole left in the ground when a large tree tips over during a high wind. Additional soil is removed so there'll be room to place the stump and the root mass. The soil removed from digging the hole is piled loosely within the reach of the excavator. He now picks up the stump and places it next to the hole. He uses care not to crush the stump with a thumb on the machine or to knock off plants and soil around the roots. The teeth on the end of the bucket are used to tip the stump over so the roots are vertical and not horizontal. The root mass is positioned so that the cut end on the stump and the cut end on the log on the ground are in line with each other. Adjusting the stump and the root mass takes a little time. We want to make sure that the cut ends are butted up against each other. We also want to make sure that they're stable and don't move if someone climbs up on the log. He turns the excavator and scoops up a bucket of soil. The soil is spread over the cuts on the stump and on the log to hide them. The soil is spread so it looks like it came out of the ground when the tree fell over. The soil placed on top of the logs will grow plants like what one sees in natural forested wetlands. It's best to place the soil loosely and not to compact it. We're also careful not to leave bucket and track marks that look artificial. The tree looks like it fell naturally across the stream and into the wetland on the other side of the stream. These photos show some of the other cedar trees we have placed in and around restored wetlands using the same technique where the root masses from cut stumps were placed adjacent to the 40-foot-long logs that were similar in diameter. It's important to place woody debris in the wetlands and streams as you're building them. This is because the ground can become too wet to return to do this at a later date. Here the excavator picks up a log and places it over the restored channel of Cambridge Creek. The log will be used by animals like a bridge to keep dry when crossing the stream. I've found it much better to be on-site working with the heavy equipment operator to place the woody debris rather than trying to draw these features on a set of engineering plans. Here's how we placed a 40-foot-long snag for the bald eagle and other birds of prey to use for a perch. 2 large excavators were used to safely install the snag. One excavator dug a long hole in the ground that was about 8 feet deep. The smaller excavator holds one end of the log in the hole as the larger excavator raises the snag into a vertical position. The large excavator uses the thumb attachment to hold the end of the log as it raises it so it's vertical. The large excavator moved backwards while cupping the top of the log in its bucket. The excavator moves on its tracks and adjusts the stick and boom until the log is vertical. Operators are very careful that the log doesn't slip and fall on their machine. Once the log is vertical, the smaller excavator places soil in the hole and around the snag and compacts this soil so the log does not move. It's possible bats will roost under the loose bark during the summer. It doesn't take long for the excavator to fill the hole around the log with soil. They did a great job because the snag is still standing after it was released by the excavator. Placing snags near the new wetland is like adding furniture to an empty room in a home. Here we're building a wetland on higher ground using the compacted clay liner technique. This is because groundwater was not present near the surface and soil that was high in clay was present in the test hole that we dug. The clay is being compacted in layers using the bucket on the excavator. Topsoil and woody debris will be placed over the compacted clay to finish the wetland. We built this small wetland using the compacted clay liner technique specifically to provide breeding habitat for the western toad. The temperature of water in the shallow basin that is supplied with surface water should be warmer than the temperature of water in those wetlands that are supplied with groundwater. The warmer water should be ideal for the development of western toad eggs and larvae. We installed buried vertical grade control structures where water entered and left each restored wetland. This was done to prevent possible head cuts downstream of the wetland from draining the wetland and possible erosion from head cuts upstream of the wetland from filling the wetland with soil. Here the excavator is installing logs to make a buried vertical grade control structure in the spillway for a wetland that was built. The operator is taking care to use sod to fill gaps around the logs and at either end of the logs to hold them in place and to prevent water from eroding a channel under the logs. The red arrow points to a buried vertical grade control structure made from logs that was built where a stream enters a restored wetland to prevent head cuts from forming. One step needed to restore the Cambridge Creek Valley involved renting large trash containers in which we could dispose of the trash that was uncovered while restoring the stream and the wetlands. We recycled all the iron that was found. We obtained many truckloads of wood slash to place throughout the restored valley. The wood was provided at no cost from trees that were cleared during construction of a new ski run near the town of Roseland. The woody material had already been piled and was scheduled to be burned. Instead, the project paid to have the slash hauled to our construction site. We placed wood slash to improve habitat for a wide variety of animals and plants and to help restrict unauthorized motor vehicle access to the restored stream and wetlands. Areas of compacted soil were prepared for the germination and growth of native vegetation using the rough and loosen technique. This method involved inserting the excavator bucket into the ground and lifting vertically, and this would fracture and loosen soil that was compacted by vehicle tires and heavy equipment tracks. Soil horizons were not intentionally mixed. The loosened soil absorbed water more effectively and provided an ideal substrate for the establishment and growth of wildflowers, trees, and shrubs. Areas treated using this technique were also far less susceptible to erosion. An additional benefit was that the loosened soil surface made it difficult for motor vehicles to traverse the area without becoming stuck. Here the excavator operator uses the thumb on the machine to loosen saturated soil. The rough and loosen technique left small pits on the surface that collected water during a rain and then injected this water into the ground. The wheel loader was used to move woody debris near to where the excavators were working to loosen the compacted soil. The excavator operator is carrying a bucket of slash to an area where the compacted soil was loosened. Operator spreads this wood in a random and a natural pattern over the surface of the ground that contains numerous pits and mounds of loosened soil. Several short sections of logs are placed in the ground as snags. These snags will provide birds with perches and discourage motor vehicle operators from trying to create a road. The excavator does not drive over the surface of the loosened ground, as this would compact the soil and it would cause erosion and reduce plant survival and growth. Here's how the west side of the valley near the road appears before the soil is loosened and the wood is spread. Here's the same area after the soil was loosened and wood slash was spread over the surface. This photo shows the east side of the valley after it's been restored. We did not want to give the off-highway vehicle riders an easy way to drive into the restored wetlands, streams, and forest. Strong action was taken to make it very difficult for unauthorized motor vehicle operators to drive around the gates that were closed. Eva Cameron worked with a team of botanical personnel to revegetate the project area with over 20 different species of native plants. The dedicated team worked to collect seeds from native plants that were already growing in the project area. They collected seeds from both aquatic and terrestrial species. They planted the seeds along the stream, in wetlands, and on higher ground. Here's how the Cambridge Creek Valley appeared shortly after construction in October 2021. We achieved our objectives of controlling erosion, saturating the deep organic soils, spreading water over the floodplain, and restoring the elevation of groundwater. A diversity of wetlands and streams have now been restored following the removal of the Cambridge Creek Dam. Zooming in, you can see the wetlands with their natural shapes and the pit and mound topography that will form the foundation for forested and wet meadow wetlands. The wetlands and streams are restored without the use of dams, berms, water control structures, pipes, or pumps that require frequent and expensive maintenance. I'd like to show you a few photos showing how the restored Cambridge Creek Valley appeared on August 12, 2023, less than 2 years after construction. The Cambridge Creek Dam was removed just to the left of the old sawmill pond. Sarah Yeomans is standing on the buried vertical grade control structure that we built with massive boulders at the downstream end of the project. There are no signs of erosion in the restored stream channel or on the floodplain of Cambridge Creek where it flowed over the removed dam. The floodplain of the stream is growing a diversity of aquatic plants. The stream has a steady flow with many pools at the driest time of year. Looking at Cambridge Creek, where it was restored in the drained basin, we see that this buried vertical grade control structure made from logs is functioning as planned. Water is flowing over the logs, and sedges and rushes are growing between and around the logs. You can't see there's a log buried across the stream with a dense growth of sedges and the willow stakes that were planted the year before. Monitoring that was done following construction showed the stream restoration structures that were made from rock that were installed at the former Cambridge Creek Reservoir and Violin Lake Dam locations were stable without notable erosion. Here's how a typical vertical grade control structure made using rock appeared 1 year after construction. However, one of the rock vertical grade control structures was found to be eroding after construction. This rock structure had been built where Cambridge Creek cut across an old corduroy road in the middle of the basin, and this formed a major head cut. The structure was repaired in October 2023. Construction started with an off-road dump truck being used to deliver boulders to the site. The excavator operator digs a deep trench across the floodplain of the stream and then places large boulders in the bottom of the trench. The excavator operator fits the rocks tightly together to form a robust buried vertical grade control structure that's wide and long and on a gradual slope. Smaller rocks are spread on the surface and embedded into the ground using the bucket on the excavator. The stream banks are also armored with rocks to protect them should a beaver build a dam across the stream at this location. The topsoil that was saved was spread over the rock. Water is now flowing over the rock in a sheet-like pattern and not causing erosion. Monitoring the first year after construction showed that many of the log structures installed using the excavator in the deep organic soils were not functioning as planned. Water had eroded channels under these logs. Some of the logs were not acting like low dams. Head cuts were able to move upstream where water is flowing under the logs. The failed logs had no water backed up behind them, and water was not flowing over the top of the logs. This problem occurred even though we had taken great care placing each log with the excavator. The excavator would dig a shallow trench in which to place the log and then pound the log into the ground. We had used the bucket on the machine along with our hands and our feet to collect and place large clumps of sedge with roots attached in and around each log, much like one does when chinking between logs on the wall of a cabin. This is what we wanted to see, the vigorous growth of plants around each log with water flowing over the log. The year after construction, this crew worked very hard to repair the failed log structures, and they did this by hand. They used techniques such as live staking willows, transplanting clumps of sedge and rushes by hand, and using shovels to dig and move soil to successfully manage erosion.
Logan is building a beaver dam. What are you doing there?
Oh, just lodging some willow whips and weaving them in between these live stakes. Then we'll stack some mud and more material, including sedge, and layering it like a lasagna or like a beaver would.
Here's how one of the structures appeared soon after it was repaired. Water was pooling upstream of the log as we watched. Following the maintenance that was completed 1 year after construction, the grade control logs and the restored stream are looking good with a diversity of plants that are well established. Beaver have taken over management and maintenance of many of the logs that were installed. You can see the low beaver dam built over this log. Beaver have placed mud and branches on top of this grade control structure that we made from alder branches and soil. Beaver have built a dam on top of this log that we buried across the stream. Here's a comparison of the drained reservoir before and after restoration. The restored Cambridge Creek is reconnected with its floodplain and is not eroding. The restored wetlands, streams, and floodplain function like a giant sponge, absorbing spring runoff and reducing downstream flooding. Cottonwood trees are growing in the valley where we loosened the compacted soil using the rough and loosen technique. The cottonwood trees are growing well in the shallow depressions we made that trap moisture. There are dense areas of cottonwood trees and sedges near the restored stream and the wetlands where there's more moisture in the ground. This ephemeral wetland recently dried. A diversity of aquatic plants are growing in this restored wet meadow wetland. It's difficult to see the grade control log in this ephemeral stream that's surrounded by sedges and rushes. The water in this ephemeral wetland has dried, so we're looking at a wet meadow wetland this time of year. This wetland that was built using the compacted clay liner technique is growing algae, which is different than the wetlands supplied primarily with groundwater. The wetlands restored in the valley look natural. Many of these restored wetlands are supplied primarily with groundwater. The wetlands are supporting a diversity of plants within 2 years of construction. The restored floodplain is both beautiful and provides essential habitat for pollinators. The snags in the water give the appearance that beaver were responsible for making the wetlands. Willow and cottonwood are growing along the banks of the restored wetlands. These wetlands were built without the use of dams, berms, diversions, water control structures, pumps, or pipes that require maintenance. The restored wetlands are working to attenuate flooding, recharge groundwater, and provide habitat for a diversity of plant and animal species. The project showed that a dam that was built over 100 years ago can be removed and a valley restored to provide habitat for a wide diversity of plants and animals. The wetlands and the streams that were restored in the valley will provide habitat to a diversity of plants and animals for countless generations.
The Cambridge Creek Restoration Project was a huge success because it involved far more than simply removing a dam. We were able to permanently control erosion in a watershed, and we were able to restore wetlands, streams, and forests in a basin that had been inundated for over 100 years. Well, if you like this video, please let us know. Hit that subscribe button so you won't miss any future episodes, and I wish you every success restoring wetlands and streams in your community.